Okay, hopefully you can all hear me. If not, just put in the chat any questions. I know Elise having issues, but welcome back, everyone. Been a big week in Ethereum and in blockchains in general, so it's kind of a fun week to be learning Solidity and learning smart contracts. So I wanted to start off with a couple of news items from the week that are kind of relevant to what we've been talking about. The first thing is we've been talking a lot about the difference between crypto exchanges where you can swap tokens for cryptocurrencies, and particularly the difference between decentralized exchanges where the entire exchange is run as a smart contract and it's kind of censorship resistant and there's no single point of failure, as opposed to centralized exchanges where it's just kind of a basic company that is running out of the UK or the US and is hosting all the server and controls who can access their exchange and has to follow the rules of the country they're in and so on. And the news that came out this week is, hopefully you can see my screen. As I was saying, so Binance, which is a cryptocurrency exchange and a centralized cryptocurrency exchange, which is one of the largest in the world, it might be the largest in the world now, was this week banned by the United Kingdom. So because it's a centralized exchange and it has to kind of follow the rules of governments and the legal system of countries rather than the rules of a smart contract, the UK was able to ban anyone in the United Kingdom from using this exchange, which obviously for Binance is not great because they lose a bunch of customers. But it also kind of shows that if you have a centralized application, it can be vulnerable to things like the government coming in and deciding that people shouldn't be using this and banning it. Or say you had a messaging app and you were trying to communicate in a country whose government didn't like any criticism. The government could come in and ban that messaging app or force the company to shut down, as opposed to a decentralized application, which is a bit more resistant to things like this. So it's kind of a cool example of some of the downsides of a centralized application. Now, the other kind of news item that I want to talk about is if you opened Remix in the last week, you might have noticed that when you go to this running tab where we've been deploying our smart contracts and sending transactions, we now have two options for the JavaScript virtual machine. So remember, this is the blockchain that runs in our browser for testing. And previously it was just JavaScript VM. Now we have a Berlin version and a London version. And what this means is that the virtual machine has now been upgraded to support the next kind of upgrade to Ethereum, which is called London. So the upgrades to Ethereum are named after different cities. Berlin is the current version, which is deployed on the Ethereum mainnet at the moment. And London is the upcoming version, which should be released this month. And you'll probably remember we talked a little bit about how a protocol like Ethereum can actually upgrade its code, because the point of a blockchain, after all, is that it requires everyone to agree to be able to upgrade any code or any rules. And the way that it works in Ethereum and a lot of cryptocurrencies is that the community agrees to do something called a hard fork. And the idea of a hard fork is you are performing the 51% attack that we've been talking about. So where 51% of the nodes decide to change the rules, but with kind of the community consent. So if enough of the miners, enough of the nodes in the Ethereum network agree that this London upgrade is good for Ethereum, then the hard fork will take effect and that upgrade will be made. So now that it's very close and London will be upgraded soon, they've added this option to Remix so that you can test your smart contracts and code and make sure that it is supported by the new London upgrade, which is cool. And also, as of last week, or as of this week actually, the Ropsten test network, which we've been connecting to. So when we go to MetaMask and we switch to Ropsten, the Ropsten Nest network has been successfully upgraded to London. So they're kind of putting it into Ropsten first before it goes to the main Ethereum network, just to make sure that everything's okay. And that's all going well so far. So hopefully London will be deployed to mainnet within a couple of weeks or so. So we can see this is, oh, everything okay? Not sure if that's a question or not. So this is the Ethereum Foundation's blog, so the kind of community organization that governs Ethereum. Tim Byko is one of the core developers. And so what happens is the community kind of decides on when to do the fork and actually change over to the new upgrade. And so they pick a block number rather than a time, because in blockchain world, time can be variable. So they've picked, say, block 1 million or block 10,499,000 for Ropsten. And then all the miners around the world agree that when we hit that block, they're going to change over to use the London rules. So that happened June 24th. There's 2 other test nets that they're running. And so these are upgrading today and this week. And then once all of these test nets have been successful, they will set a block for mainnet and it will be upgraded, which is cool. And to kind of make sure that everybody is following the new rules, all of the different clients, so all of the different node types for Ethereum with different development teams, have to make sure that they've upgraded their client to be able to support the new rules. So you have to make sure you've updated your node to make sure that you don't kind of lose connection to the network when the hard fork occurs. But since we're using MetaMask, which handles the nodes for us, we can just continue on without having to worry about that. So it's very easy for a user. It's a little bit more complicated if you're a miner. Now, the kind of big ticket item in the London upgrade, which is interesting to us because it changes something that we've been talking about, is this Ethereum improvement proposal 1559. And what this does is it changes the way that gas works in Ethereum. So this is just for interest. You probably don't need to remember this, but we talked before about how a block has a gas limit, and the gas limit restricts how many transactions can run in that block. So if you're generating a block every 2 seconds, it might fit 12 transactions every 2 seconds. So what EIP 1559 does is it makes that gas limit no longer set to be an exact limit. It can actually change over time depending on demand. So if there are just like a normal amount of people accessing the Ethereum network, it will stay about the same as it currently is. But if suddenly there's a new hot crypto app and everybody wants to be sending transactions all at once, that gas limit can now dynamically increase so we can fit more transactions in a same block and effectively go up to double the normal block size. So you can have double the transactions for a period of time. So it should help kind of scale the Ethereum network for the next 6 months or so and make sure that it can kind of keep up with increased demand. So it's quite cool. There's some other kind of little features and we don't really need to worry about those, but EIP 1559 is the big one. Okay. So what we kind of talked about last week was we really got into how we actually start to develop smart contracts. And we talked about the basic features of the Solidity language. So I'll bring up my slides again. You've got your contracts, which are like objects. You've got your state variables, which are put into storage, and that's where you can kind of keep data in the blockchain that persists between transactions. Then you've got your memory, which can be used during a transaction and is then discarded at the end. So we talked about all that. Then kind of the main thing that we wanted to go through was these smart contract principles, which help us develop smart contracts and kind of specify the way that smart contract development differs from regular application development, whether you're building an app or a web service or something like that. So we looked at choosing efficient data structures, preferring things that have a constant time rather than looping through arrays, for example, or doing big complicated computations all at once. And as part of that, we looked at also at amortizing the work. So this is spreading the work around between multiple transactions so that everybody kind of contributes a little bit of the cost of running that transaction. What I wanted to do today is to finish off these last two smart contract principles. So we'll start with this second one, thinking in state machines, which I'll go into. And then we'll talk a little bit more about the conditions, effects, interactions pattern, which I talked about last week. And in particular, we're going to be learning today how we can have smart contracts that interact with each other. So far we've dealt with single contracts, which normal people or normal users are interacting with each other as part of. But the kind of Ethereum selling point is that all of these contracts can start to work together. So you can have a decentralized exchange contract talking to a token contract, talking to a loan contract, talking to a user, right? And they can all kind of interoperate and call each other. And so we'll learn how to do that today. And as always, any questions, either say it in the audio or put in chat, and I will stop for that. So with that being said, let's get into it. First thing up, we're going to be talking about state machines. And a state machine is almost a concept or a modeling concept that I think really efficiently describes how we write smart contracts. So what I'm going to do is I'll just do a little diagram as part of this. So forgive me if you already know what a state machine is. I won't go into it in too much detail. The idea of a state machine is that we have a bunch of kind of states or current positions that our program is in. So let's say we have state A, B, C, D. And our computer program can only be in one of these states at a time. So if it's in state A, right, it can't be in C, B, or D. Then between these states, we have what are called transitions. And a transition is like an arrow that says that if you're in state A and you have a transition to B, you can move along that arrow to change to state B. So our state machine might look like this, for example. So this state machine says that if we start off in state A, we can only move to B. Then from B, we can go to D, then C, then B, right? And we can keep going around this loop as much as we want. We might also have a transition that goes from D to B. So then when you go A, B to D, you now have a choice. Will you go back to B or will you go to C, right? Then the final kind of transition we have is you might have a transition to yourself, which I can't get to draw nicely. There we go, right? So you can be in B, you can perform some action and you can stay in state B. And what's really great about applying state machines to smart contracts is that a smart contract generally models processes or applications that take place over time. So if you think about our auction contract, for example, we kind of have these phases where everybody is bidding, then the bidder is revealed and the auction is won, then people can withdraw their money. So it can be helpful to kind of plot out our smart contracts logic as a state machine before we even start implementing it, so that we can kind of see how to represent it cleanly in code. So if we think back to our auction, the simple auction contract that we built last week looked something like this. So we kind of had the first state, which was called bidding, or we might also call that open. Then we had ended. Then we had withdrawals, right? So once the auction was completed, anyone who lost their bid could withdraw their money. So it was really a simple state machine that looked like this. Then on these arrows, we can start to put different conditions or actions that take place to actually make that transition. So when we're in the bidding phase, in order to get to the ended phase, what happened was we went past a certain block. So we went past a certain time, which was the auction period ending, and that's what allowed this transition to occur. So we kind of had this, this auction and time passed, right? We have this condition on the transition, it looked like this. And then this transition, so from the ended state where we pay out the winner and we then go on to the withdrawal, this was just automatic after that. Hopefully people will remember how the simple auction worked. We also had, if you remember, the kind of operations that could take place within these states. When we were in this bidding phase here, we were able to make a bid, right? And that is a transition that looks like this. Because if someone calls this contract and goes bid, it's changing the current storage value of the contract, right? It's storing their bid in the contract, but we're still remaining in that bidding state. And the same is true for withdrawals. So if someone were to withdraw, it just looks like this. So if you've actually modeled out your smart contract as a state machine before even going into development, it's pretty easy to translate this over to the code. Right? The hard part is the design and thinking phase, and then you can make the code pretty easily. So what I wanted to do to start off with and to show how this kind of state machine based development process works is we're going to start off with extending our auction contract into what's called a blind auction. So if you're selling a house or you're selling a bunch of sheep, the way that auctions traditionally work in a simple auction is everybody's kind of standing around. The auctioneer will say, I want 1 million. Someone will raise their hand and bid 1 million. Then everybody knows we're up to 1 million. Someone raises to 1.2 million, then 1.3 million, and finally it's sold for 1.5 million. And what that is really good for is the buyer. If I came to a house auction and I was willing to bid if I was willing to pay, say, $2 million for the house, if the bidding only got up to 1.3 million, and I said, okay, I'll go 1.3 million, and then nobody else was willing to bid, I've paid 1.3 million for the house and essentially saved myself $700,000. But for the seller, it's because I was willing to pay 2 million in the first place, the seller would much prefer that I paid $2 million, my maximum amount. And so to kind of get around that problem where the auction favors the buyer and change it so the auction favors the seller, we have what's called a blind auction. And the blind auction modifies this structure slightly. So as you probably guessed, the key difference is that nobody knows anyone's bids until the end of the auction. So we have a new phase between bidding and ended. In the bidding phase, people are submitting bids, but they're called sealed bids. So they're actually hidden from everyone else, and they're hidden from the person conducting the auction. Then we move to a new phase, which we're going to put into here, where everybody reveals the bid that they put in previously. So then everybody knows all the bids. Then it just continues as normal, right? We've ended the auction and we pick the person with the highest bid. But because when you're bidding, you don't know anybody else's bid, you are always incentivized to put in the maximum price you're willing to pay. So if it's 2 million for me, I'll put in a bid for $2 million. That's easy enough. Does that make sense? Let me know if it doesn't. So the only thing we've got is a new condition on this transition here, which we'll call bidding end time passed. And then we can change this transition to be reveal end time passed. So we've kind of got now these two phases of bidding. You submit the bid and then you reveal it. So what we're going to do is we will build a blind auction smart contract, but we're going to do it in a way that kind of shows the first instance of how we start to build in private data into a smart contract. So you remember that once data has gone into a smart contract, it's public, right? Anyone who's connected to the Ethereum network can read what's in the smart contract storage and would theoretically be able to see everyone's bids. So we need a way to be able to submit a sealed bid and then reveal it later. And as with a lot of cryptography and a lot of blockchain applications, the answer to this is in something that we've dealt with previously, dealt with a lot. And the answer to do a sealed bid on a blockchain is a hash function. So if we think back to our SHA-256 or KEKAK-256 in Ethereum, the hash function is just that one-way function. So it takes whatever you put in, it spits out a hash of it, but you can't go the other way. So what we could do to submit a sealed bid is we could say hash the amount of money that we were willing to pay. So if it was 2 million, I would put in 2 million, and then I would submit that hash onto the contract. That's my sealed bid. So nobody else can tell what I bid. But then in the reveal phase, when everybody's revealing what their bid was, I put in 2 million to the contract, or put in this number. It will hash it. It will compare it with my bid in the bidding phase, and if it matches, it will accept it. Right. So I'm kind of revealing the value that created this hash, because there's no way for the smart contract or for anyone else to go in the opposite direction. So that is, that's perfectly hidden if you're submitting this hash and then revealing it later. There is one issue with Ethereum, and that is, if you remember the simple auction, we wanted people to submit the actual amount of ether that they were bidding ahead of time and then withdraw it afterwards if it failed, so that when the auction concluded, the payment was automatic. If we were doing this kind of sealed bid system just with a hash, someone would submit this hash, but they would also have to submit $2 million of Ethereum to the contract at the same time. People would be able to see how much money that was. So as kind of an extra security mechanism, what we're going to allow people to do is make multiple bids. So they'll be able to submit multiple sealed bids, and they can send in any amount of ether they want as long as it's higher than their bid. So if I was willing to bid $2 million, I might secretly, to kind of hide that, send a $1 million bid and a $4 million bid, and then a $2 million bid that I've added $3 million of Ethereum to. And that might sound confusing, but it should make sense when we look at the contract. And then in the reveal phase, I reveal that my true bid was the $2 million one, and then all that other money will be refunded to me. So it's a way of kind of hiding my bid amount during that contract reveal process. Okay, so we're also going to see some new Solidity features as part of this contract. So I'll talk through them when we get there. All right, let's go over to Trusty Remix. I'll stay on Berlin for now. There's no real difference for our smart contracts, but stick with what you know. And what I'm going to do is create a new contract now that I'll call Blind Auction. I'm just going to copy in the Solidity Pragma line, which tells me what version of Solidity we're using. And then I've kind of pre-written an interface for this. So remember we talked about the interface being that, it's like the interface in Java, right? It tells you what functions are available on the smart contract, and then you can implement them later. So just as our state machine foresaw, we're going to have a bid function, then a reveal function, then a withdraw, and also an auction end to actually finish that auction. And we'll throw one event, auction ended, which tells everyone who the winner was. So if we look first at this bid function here, we can see we're only passing in one value, and that is that hashed bid, right? So that is that 32-byte hash of our bid amount. That's all that we need to pass into bid, but we've marked it payable so that we can send Ethereum along with that. Then to reveal it, what we do is we pass in, we pass in all the values of our different bids. So that's one real bid, one fake bid. And then we pass in an array of booleans, which say whether or not the bid was fake. So maybe for illustration, I'm willing to pay 2 million. So I'm going to send 3 bids that look like this to confuse people. Now they don't know which one's real. And when I reveal it, I'm going to pass in true, true, false, true. And this is saying that this bid here were fake, discard them, refund me. this is the real bid that I want to reveal to people. And then the final argument that we want to pass in is a secret. And the reason for the secret is to defeat one more kind of way of analyzing and working out what people's bids are before the reveal. And that is illustratable if we just start looking at this. So if I put in 1, I can see that my hash starts with C89. If I put in 2, it's AD7, so on, right? There's no way to predict it going backwards. However, if I am selling a house, I know that the bids might be in the range of $1 to $2 million. And if I want to know what everyone else is bidding, it's really easy for me to, on my computer, write a program that will really quickly work out the hash for every number between 1 and 2 million, store them, and then look at everyone's hash bids and see, oh, C5D, that's 2. They've bid $2. So to combat that, what we do is we submit our bid with our own personal secret added on the end. So if my secret is Cadle, that changes the hash so that nobody can kind of pre-compute all of the hashes and then compare that and know that I've put in 2 as my bid. And the reveal still works, but I have to pass in that secret at the same time. So hopefully that makes sense. Then the withdraw and the auction end functions work exactly the same as the simple bid. Okay, so let's get coding. This is all the standard stuff, right? So we're going to start off implementing this interface. And as always, we'll start with what we're actually going to be storing. So something interesting here is that we need to store the bid hash or the blind bid. And we also need to store how much money was sent along with that bid, or how much Ethereum was sent with that bid. Now we could do that like this. We have a mapping from, say, address to bytes 32 and call that blind bids. And we could then have a mapping from maybe bytes 32, which is the bid, to the deposit amount, like that. But since this information should always be kept together, for every bid we want to get the deposit, the same, it can be helpful to kind of group these variables together. And to do that, we'll use something called a struct. This is a struct in C. It's a struct in C#. In Java, it's a data transfer object or a record or something like that. And we'll call our struct bid. And what this lets us do is group together values. So I'm going to say a bid is comprised of that hash, which we'll call the blinded bid, and the deposit amount, which is like this. So struct bid here is now declaring a new type, which is a group of values containing these 2 variables. Then to store the bid, what we can do is we can map the address of whoever submitted the bid to this bid struct. Right? So this struct can be a value in the mapping, just like other things, or it's public, and it could look like that. The interesting thing is we want to be able to support people making multiple bids. So we can really easily just change this so that the mapping goes from the person who submitted the bid to all the bids they've submitted. And then they reveal all of those bids at once by passing in those values as an array. Okay. Then paste in these. These are all very, very similar to the simple auction contract. So we want to store the beneficiary, who's going to receive the funds from the auction when it's completed, so the house seller. We're going to store the block number when we should finish the bidding phase, so when we should move from open or bidding to reveal. And then we're also going to store the block number where we're moving from reveal to auction ended. When the auction has ended, we set this Boolean to be true. And since we're in the, we want to remember later what we've done this for, we're going to call these state machine variables, something like that, because they tell us what state we're currently in. Okay. Then also copied from the last contract, we'll have the current highest bidder and the current highest bid, which we'll calculate in the reveal stage. And then we'll also have the withdrawals that are waiting to happen. Okay. And so that should be all we need to store in this contract. The constructor is, again, super simple, super similar to how we did it for the simple auction. So whoever sets up this auction is going to specify how long the bidding phase lasts for, how long the reveal phase lasts for, and who will be paid at the end of the auction. And then we just copy these values from memory inside the function to storage so that they persist once the contract is created. Now we'll get to the more interesting functions, which we'll actually implement from scratch. So the first one up here is bid. Right here, we're going to be passing in a blinded bid, so that hash, and we're going to be storing it as a bid for the sender. So I'll copy in my bid signature, or my bid interface. I'll start implementing it. See if I save it, it'll remind me that I need to put an override because it's in the interface. So let's do that. And we've also marked this function as payable so that people can send Ethereum to it. So when we get in our new bid, what we want to do is create a new bid in that bid array for whoever's sending it. So remember to access in the mapping, to look up in the mapping by address, we'll use square brackets. So we'll go look up the current bids for message.sender, or the account who's sending this transaction. And then what we want to do is add a new bid struct to the bid array for that sender. To do that, we can use push, and push just adds a value to a new array. If necessary, it will add more space in the array. So if you start with an array of size 1 and you use push, it will extend that array for you. You don't have to worry about doing that manually. And we're going to create a new struct using that type that we created before. So using the name of the struct. And then we'll pass in the two values. So blinded bid first. Now we know this is the hash. This is the blinded bid being passed in. And the deposit. The deposit is the amount of Ethereum that was sent to this bid function. And if we remember going back to the solidity documentation, we can get that with message.value like this. So that actually should be all we need for the bid function, right? Someone passes in a hash and sends money along with it. And then we want to store it for, in that mapping, in that bids mapping, so that it can be revealed later. In general, if you want any information about the current transaction, so who's sending it, the value, how much gas is left, things like that, it'll be message.something. Message is the same as transaction in this case. And if you want information about the current block in the blockchain, you'll go block.something. So to work out when bidding ends, we're adding on the bidding time period to the current block timestamp. So hopefully that makes sense. Now, once we've written this bid function, we kind of want to check our state machine that we've previously designed to make sure that it's implemented correctly. And if I look at the state machine here and kind of compare it to the code, we can see already that we've made one kind of oversight. And that is that our bid function can accept bids at any time. So this bid action can run at any time. But in our diagram, we're saying that the bid function can only occur in the bidding state. Once we've moved on to reveal and ended and withdrawals, we can no longer use this bid transition. So we want to restrict the function by adding a condition on it, as we've done before. We could do this using a require function. So remember, we'll put any requirements at the start of the function. We'll put our conditions there. And we're requiring here that we're still in that bidding phase. So the current timestamp is before bidding end. And that would just look like this block.timestamp. So the current timestamp is less than bidding end. And we can say Otherwise, the bidding phase is over. Right, you could do like that. Since we've got a multi-stage state machine with a bunch of conditions that look like this, we're going to simplify this a little bit, and we're going to use those modifiers that we saw last week. So we can think of all of these phases here, bidding, reveal, ended, have a kind of time where they can be run, and then a time after which they cannot be run. So the bidding phase can only be run until bidding end. Reveal phase can be run between bidding end and reveal end, and then ended runs after reveal end. So remember, a modifier is like a way to modify a bunch of functions at once. Rather than adding the required to all of these functions, we can use them to kind of generalize that condition across all of our different states. So I'm going to create a couple of really simple modifiers here. I'm going to call one only before. And we're going to extend our knowledge of modifiers by adding in now an argument to the modifier. So previously, when we were dealing with access control, I think we had like an isAdmin modifier, which looks something like that. But our modifiers, just like functions, can actually take in arguments. So here I'm going to call my modifier only before, and it's going to pass in a time. Then in the implementation, I'm going to move this requirement to here. I'll change this to use whatever time was passed in. We are saying that to run this function, the current block timestamp has to be less than whatever was specified as the argument. And I'll just say change this to stage is over. Then we fill in the rest of the function with that underscore character like that. So our bidding end function, our bid function here, which has to run before bidding end, we can now really easily add that condition using only before and passing in bidding end. And because bidding end is a storage variable, it's stored in the contract, we can use it as part of the function definition. So that's a really cool way to kind of share complicated conditions across all of your functions. So I'll pause there, see if anyone has any questions before we get to reveal, which is the most complicated part. Okay, cool. So reveal is a little bit more complicated. And then we'll just see withdrawal and end are the same as the simple option. I'll paste in the interface for reveal. And just because it's hard to read, I'll make that go over multiple lines. Okay, so firstly, we have to override this because it's part of the interface. Now, what we want to do when we reveal is we're going to add that same sort of condition, right? It's a time-based condition. It can only be done before the end of the reveal phase, so only before reveal end. But it could also only be done after the end of bidding, right? It's kind of sandwiched in between the bidding and the end phases. So we'll create another modifier, and we'll just copy this, and we'll call this one only after. We'll just change the direction of this, so the block timestamp has to be after whatever time we pass in. And we'll change our error message to be stage hasn't started yet. So now we can only run this before end of reveal, and we can only run it after end of bidding. Right, so we've kind of already encoded that state machine information just in that function definition there. And once we start to get a bunch of modifiers to the function like this, it's kind of good Solidity practice to put them all on separate lines so that it's a bit easier to read. So we'd write it like this. It's not strictly necessary, but generally if you see a smart contract, it'll be written in that style. So the first thing we're going to do is we'll use again that conditions effects interactions pattern. like this. Now, remember, people can submit multiple bids and then they reveal them all at once by passing in arrays here. So our only real condition, firstly, is to make sure that all of these arrays have the same length as the number of bids that someone's passed in. So this is quite simple to write. We're going to store the length of, or the number of bids that this caller has already submitted. So we'll look up their bids array by their address, and then we'll just use dot length to get the length of it. All right, that's pretty standard. Now our condition is that, say, the number of values that they pass in, so the number of bid amounts they pass in, values.length, is equal to the number of bids. And we'll copy this and we'll do the same for the fake array, the same for the secret array. Hopefully that's quite simple. Now, next, what we want to do is we're going to reveal the bids and we're going to then place the actual bid. So in the simple auction, we saw that when the bid was placed, we're going to kind of update the highest bidder and so on. But we only really want to place the real bid, so ones that aren't marked as fake. All the other bids we wanted to refund. So in this effect, what we're going to do is use a little loop that will mean that we can refund all the fake bids and actually place the real bid. Now, there are probably ways to do this without using a loop. You know, we talked about loops being not the best for Ethereum and smart contract development because of the gas limit. If you made an array that was really long, you could always hit the gas limit when you called this function and break the contract. However, in this case, because the loop only runs over the bids submitted by a certain person, if a person submits heaps and heaps of bids, they've only blocked themselves from revealing the bids. They haven't blocked everyone else. So it's kind of a bit safer, and that's why we're going to use it now. So what we're going to do is kind of build up the refund by looping through that bids array, and we can do it like this. So for uint 0, I is less than length, their number of bids, plus plus. Okay, now what we're going to do is we want to go bid to check equals accessing all their bids and then getting, you know, the ith bid. We're looping through them, and we want to save this bid to check variable so that we can kind of, you know, check different fields on it. We declare the type as a bid struct, but there is something slightly more complicated when we start to deal with structs, and that is that we can't keep them in memory. So if we are if we want to save a bid or another struct as part of our function operation, we have to keep it in storage rather than just letting Ethereum hold it in memory. And to do that, I will just add this storage modifier. So we saw that when we passed in arrays previously, just like here, we've made sure that Ethereum knows to put them in memory. Here, we're going to be storing whatever the current bid that we're checking is in storage. Okay. So what we're going to do now is we're going to assign multiple variables at once in memory. So we get the value, whether the bid is fake, and then the secret that was sent with the bid as part of the hash. Like this. So values I, then fake I, then secret I. So this is just combining those variable declarations into one, just to make it a bit easier. Okay, now we're going to look at the current bid. And what we want to do is check that the hash that has been submitted, so the sealed bid, is equal to the hash of the value, whether or not it's fake, and the secret. So you can think if I'm submitting a bid of 2, that is the real bid, it might look like this, you know, 2 true and cable's my secret. Or 2, sorry, if it's fake, it'll say true. If it's real, it will say false. Okay. So we want to take these three variables, value, fake, and secret, get the hash of them as part of the smart contract function, and compare it to bid to check dot blinded bid, right, which is that hash that has been previously submitted. So if it's not equal, so we're going to do kecat256. This is that hash function that we've been using. And as a reminder, kecat256 is very similar to SHA or SHA256, which is a more commonly used hash, but it's a little bit more efficient for Ethereum. And in here, we would pass in value, fake, and secret like that, right, in an ideal world. There's one complication in Ethereum, which is value, fake, and secret might all be of different lengths. Right, so value is 256 bits. It's a uint256, so that's the default. Bool, which is a Boolean true or false. I actually don't know how many bits, if that's 1 bit or 8 bits. It might be 8 bits. And then bytes 32 is 32 bytes. Right, so what we want to do is kind of combine these all together to do the hash. And we'll use the very confusingly named function abi.encodePact. Like that. So what encodePact does is, and this is only interesting if you know a little bit about low-level development. So if you don't, you can just ignore what's actually going on behind the scenes. The upshot is that abi.encodePact smooshes these variables together. But where it's useful is, say we have the variable that looks like this. Sorry, I'm doing it in binary now, so zeros and ones. I'll go 0, 0, 1, 0, 0, 0, right? So that's 8 bits. 8 bits for the second variable. It's 8 bits, right? So these are 4 variables. In kind of low-level virtual machines like the Ethereum one, we have what's called like a word size or a register size. And in Ethereum's case, it has 256-bit words, which means usually that if you were to kind of store these 4 bytes into memory, they would have to be aligned to multiples of 256. So you would have, firstly, this variable, which is 8 bits, followed by then, 248 zeros. They look like this. And then you'd have to do this for all of them. So to store your 4 bytes, you've ended up using 32 bytes. That's quite wasteful. And this is called word-aligned storage, so like that. But what encodePact does, so when we're using this abi.encodePact function, is it ignores the kind of alignments and it will just stick them all together. So we'll go 0, like this, and then it will fill in the rest of the word. But you can see it's been combined kind of into that single variable. And then we can pass that into the hash function. So that's a bit of a diversion, but hopefully interesting. So we're essentially taking the value of the bid, whether it's fake or not, the secret, and we're checking it with the blinded bid. Okay, so if it matches, then we'll start doing all the revealing logic. But if it doesn't match, so in here, we're just going to ignore this bid, right? It's not a valid bid, so we'll just kind of skip to the next bid, right? Continue, like in Java, just goes to the next iteration of the loop. Okay. Now, our refund is going to be incremented or added to by the amount that was deposited as part of the bid. Then what we're going to do is check whether this is a real or a fake bid. And if it's real, we'll actually submit it. So if it's not fake, and remember, we're also requiring them to deposit more than or equal to the value of the bid that they've specified. So if that's true, then we're going to attempt to place the bid. So attempt to make the bid as the highest one. So I'll implement this function in a second. Make bid. And if that works successfully, then we'll take that back out of the refund. Otherwise, it's still in the refund. And finally, what we're going to do is kind of zero out and empty this bid. So we've checked it. We want to make it 0 so that we're not looping through it again. And because we've defined this bid as being in storage rather than in memory, we can actually modify it directly by using a dot bid to check dot blinded bid, and it's equal to all zeros. So 0 as plus 32. Finally, right at the end of this function, we're going to do our interactions. And the interaction is to transfer whoever called this their refund, which in this case will be message.sender. So remember, message.sender is an address. If we want to be able to pay the address or transfer it to Ethereum, we have to make it payable to have done that. And then we'll call the transfer function with the amount of Ethereum we want to refund, and that will be sent from the contract, from the contracts of Ethereum. Now, place bid, which it's complaining about because we haven't made it, is exactly the same or almost exactly the same as our simple auction. So I'm just going to copy and paste that in. So we don't have to go through writing it, but it's just going to override the highest bid if it's the highest. And then what I'll also do is finally build in that kind of auction end function, which is again copied from simple auction. We call this function when the reveal phase is complete. So I've added in that only after modifier. So it can only be run after reveal ends. This will move us into that auction ended state. And will emit that event and transfer the beneficiary how much money they've earned or they've won from the auction. And then finally, we've been building up this pending returns mapping, which kind of says who is owed what, and we're going to allow people to withdraw from that function. And so again, I'll just copy in withdraw. The problem with withdraw is that we want it to only occur after the auction is ended. So again, we'll use that only after reveal end modifier. Okay. And so that has built up our blind auction contract. And we can then compare it to our state machine when we're showing to people and explaining to users how to interact with it. And it kind of, it's a nice way to encode that logic on the smart contract. So are there any questions about, the blind auction and how that we kind of modeled that? Okay, cool. So I'll send all these contracts afterwards so you can go through it in a bit more detail. I know we just kind of pasted in a few functions from our previous contract there for the sake of time. But that's a good illustration of our thinking in state machines principle. Once we get into, say, more complicated contracts like a decentralized autonomous organization where there's voting and things like that, these state machines become a lot less linear. They have branching and things like that. You might have the state machine looks like voting open. Then you've got counting votes. You might have a branch that says vote success, a branch for vote failure that mean different things. And so you end up with a more complicated diagram. But for now, we've been doing simple things, which is good. Now, what I want to talk about for the rest of today is how we can start to extend these contracts, as I said, to interact with other contracts. So we've talked already about the purpose of standards in contracts, like the ERC20 token standard. is that then other contracts and other applications can all rely on that standard to interact with the token and to kind of use it for its own purposes. So what we're going to write now is a new contract that's going to allow a group of people who go out to a restaurant to split the bill at the end of the meal. Rather than everyone trying to pay cash to the person who paid and then having to give change and so on, we all know it's a pain in the bum. So what we're going to do is we will kind of build that into a smart contract where people can say an amount that they've paid. It'll be split between all the addresses that they provide, and then it'll do that token transfer all at once. Now, the token in question that we're going to be using for the sake of argument is Cadle coin, which you might remember from a couple of weeks ago. It's our own ERC20 token that we've set up, like it's a really standard thing. And it follows this ERC20 interface, which is the same as all other Ethereum fungible, mixable tokens. But because we're using this standard, we don't actually have to say that our contract only interacts with Cadle coin, right? It could interact with the Uniswap token or a stable coin. It's like kind of generic to all of these different token types. So even though we'll use Cadle coin as the example, we can use this for anything. Call this split my bill. Okay. So we'll just start off as is standard. We'll call split my bill as the contract. And we will start off really quickly storing our state. So we're going to store the amount that we want to split. So if we're at the restaurant, it costs $200 for everyone, for a group of 5 people. So then we're going to store the address of all the different people who are at the restaurant. So we're going to store an array of addresses, and we're going to call this split between. So if your address is in this array, then you're going to be helping to pay the bill. Then finally, we're going to give the address of the restaurant. And the restaurant will actually receive the token. Now, the final thing that we want to do here is we're going to store the address of the token contract on chain that we can use to pay the restaurant. And we're going to make this a variable that's stored in the contract so that we can make the payment in any token that we want, rather than just Ethereum. So we'll call it token. It's public, so anyone can see what currency we're using. But the type of this variable, this token, is a bit more interesting. Because Solidity is quite a high-level language, what we really want to do is allow token to be anything that conforms to that ERC20 standard. And you might remember in Cadle coin, we wrote this interface ERC20. So we're going to make that the type of our token variable, like this. So now the variable in here is the address of any contract that implements the ERC20 interface. So it will have a transfer function. It will have an approve function, transfer from, balance of, things like that. And so that the Solidity compiler knows where we're getting this ERC20 definition from. We know it's in the Cadle coin file. So we can actually start to create a multi-file application by adding an import at the top. And this is very similar to how JavaScript and Node does it. I just give it the path to my Solidity file that I want to import. And so I'm importing Cadle coin. I get then access to, I get access to ERC20 and Cadle coin in my split the bill. Right, so now that will compile. Cool, so the constructor is very straightforward. I'll copy and paste this one in probably. Right, we're just setting in that. We're passing in the address of the restaurant, the amount that we spent, all the people that we're splitting it between, and we're passing in the address of the token that we want to use. The only kind of interesting thing here is when we're calculating the split amount, so how much each person has to pay, we're dividing the total amount by the number of people paying. Okay. So once this contract's been set up, to actually run it, we're going to have this function split, which is public, so anyone can call it. And this function here has to actually transfer the money on behalf of each of these people in the split between array to the restaurant. So it's kind of a transfer from each of those people. And in order to do this with a token, what we'll do first is kind of look at our token interface and work out which function is the best. So we're doing a transfer. We've got two functions here that allow us to do transfer. We've got transfer, which sends from whoever is calling this token will be sending the money. Then we have, more interestingly, transfer from. And transfer from lets you put in the address that you're sending from, the recipient address, and then the amount to transfer. And if you've previously been approved to spend money on behalf of that sender address, it will make that transfer. So our split my bill contract is going to use this transfer from function in the token to actually make that payment. So it's super simple. We'll have a loop like this. So you're very familiar with this by now. We're going to loop through all the different people to pay. Now we've got our token IERC20, and because we've defined this as the interface type, Solidity is smart enough to just let us call functions on that contract as if they were a regular function. So we're going to use transfer from. We want to transfer from the account of the person that's being split from. We want to transfer to the restaurant, and we're going to transfer that split amount. So that's actually super easy, right? We're calling a new contract now, just using that interface that we specified, and it'll make that transfer. Then there's one more thing that we'll add to this function. Because split my bill is kind of designed to run once and then we're not going to reuse it, we can get a little bit of gas back. So we can return a little bit of the money we've spent by using something called self-destruct. And self-destruct is a function that will remove this contract from the blockchain. So it'll still kind of be there in the history, but going forward, all of the storage that is taken up by this contract will be deleted. And as a reward, we get a little bit of gas back, a little bit of ether back, and that will go to whatever address you put into the self-destruct function, which in this case, we will reward whoever calls the split function. So we do it like this. Okay, so we've now got our whole split my bill contract that is interacting with that token. Now what I want to do is kind of show how we would start to use this when multiple tokens are involved. So I've compiled in this second tab. I'll compile split my bill. That's ready to go. And I've also compiled Cadle coin before. So I can do that again by just saving the Cadle coin. And like we did when we were demonstrating tokens, the first thing I'm going to do is from what we'll call account number 1, I'm going to deploy this Cadle coin token. I'll say we've got 1,000 total Cadle coin available. And I'm going to deploy the token to here. So this token is now a smart contract on the blockchain. It has an address and it has these functions available. Then what I'm also going to do is we've all gone to a restaurant. We've agreed that we're going to split the bill. So I'm going to deploy this split my bill contract, which will appear once I've saved it. So I've switched contract here to split my bill. And in the constructor, we've specified that it needs a few arguments. It needs an address to pay to, so this is the restaurant. Maybe we'll say that this last address in the list is the restaurant. So we'll copy that address, paste that in as the restaurant address. And we say our meal is worth 200 Cadle coin. Then we're going to split it between two addresses, which might be, me and my friend. So I'll copy in my address. And I'll copy in the second address here. Sorry. Okay, and now the final argument is the most interesting one. That is our ERC20 token contract. It's asking for an address, and this is, again, any address that meets that ERC20 interface. In our case, our Cablecoin contract does that meet that interface. So we can copy its blockchain address and provide that to our smart contract so it knows which token to use to pay. So this is the address, just like we have our account address. And I'll transact that, and we've now got our split bill contract ready to run. Right, so I can see who the restaurant is. I can see that we'll each be paying 100 Cablecoin and so on, which is really cool. Now, if I call my split function, it will fail. So I've called this. We don't get much helpful information because we haven't added in any kind of requires or things like that. But if you remember before, our transfer from function in the ERC20 interface requires that everybody kind of approve this contract to spend our money. So as the first person, I'm going to approve the split my bill contract to spend up to 100 Cablecoin that are in my account. So I'm going to interact with the Cablecoin contract. And I'm now going to approve the spending of 100 tokens by whatever person or contract I want to be able to spend it, which in this case is split my bill. Right, so we can see the interactions between the contracts start to become multi-level. And again, I'll just use the address of split my bill. I'll paste that in here, and I'll send that to the token contract so that the token contract knows that it can spend up to 100. That knows that split my bill can spend up to 100 of my coins. Now I need to do the same for the second account. Oh, I've already done it for the same account. Let me do it for the first account as well. And I'll also need to actually make sure that the second account has some money. So I'll just send it, say, 500 Cablecoins from whoever deployed the Cablecoin contract. Okay. Now, this should be all ready to execute. So for the split function, we've both made our approval. So the two contracts here have made their approval. We've set the restaurant, we've set the amount to pay. If I call split, it should kind of interact with that token contract and actually make the transfer. So let's see if we've done anything right or wrong. Call split, there we go, it's succeeded. So if I check my balance now, I should see that it has gone down to 400 tokens because I've spent 100. So if I go back to the Cablecoin contract, I call balance of, and I'm going to put in my address. Great, it's at 400, so I've transferred 100. And if I check the balance of the restaurant, which is this last address, again, use balance of, we can see the restaurant has been paid that 200. So by allowing our smart contract to start interacting with that currency, we've programmed that financial transaction between two friends in this case, could be 100 people, and kind of automated that on the blockchain. So that's pretty cool. Are there any questions there about how we kind of interact with other smart contracts? Yeah, awesome. So now we're going to extend this with a slightly different example, but we're going to use an example that really highlights the importance of this conditions effects interactions pattern. So I talked a little bit last week about how this kind of is really important to make sure that your smart contract can't be attacked. And I think I called the type of attack last week a replay attack, but that's actually not correct. It is a re-entrancy attack. Sorry, I'll put it there. So apologies for that. Replay attack is a slightly different type, which I might talk about another time, but this pattern is vitally important to defeat a re-entrancy attack. And a re-entrancy attack is possible once we have contracts that call other contracts. So what I wanted to do is demonstrate firstly a contract that is vulnerable to this attack. And then I will demonstrate a contract that is it's fixed by using this pattern and by using a different technique. So hopefully this makes sense. I'm going to delete those contracts just so we don't get confused. So we'll start off from scratch. I'm going to create a new contract. All this, sorry, it's in the wrong folder. Now what I'm going to do is call this contract share cash. And this is kind of the opposite of splitting a bill. What it's going to do is will let me kind of pay a certain amount of Ethereum, say 100 Ethereum, and a list of people that I want to share it with. And then it's going to split that Ethereum and send it to each person, basically. So if I'm feeling really generous and I want to split my 100 Ethereum amongst all the participants of this call, I might use this smart contract. So to start off, I'll copy to save us some time. Our contract is here, our share cash contract. We'll have one kind of storage variable, which in this case is a mapping of balances. So the person who is owed to how much they currently owe. Then in the constructor, I'm going to pass in a list of the people that I want to share my Ethereum with. And I've also marked this constructor as payable so that I can send Ether to the contract. Then I'm going to loop through this list of people that I'm sharing with. And to each of them, I'm going to add to their balance the total amount of Ethereum that I've sent divided by the number of people I'm sharing with. So hopefully that's pretty straightforward by now. We will also add this total balance function, which is just kind of a convenience thing so that we can see how much money is, or how much Ethereum is currently held by the contract, which we can use for debugging. So again, it's a view function, which means it doesn't update any state. All we're kind of doing is we want to return the current balance. And to do that, we're going to look at the .balance variable, which is available on any address. And we're going to ask for the address of this smart contract. So address this just means give me the address on the blockchain where this contract is stored, and then look at the balance. So how much Ethereum the contract currently holds. Okay. Now the interesting function here is called withdraw. So just like the auction contract, the way this is going to work is that we will add a certain amount of Ether to everyone's balances. And then when they want to take that out of the contract, they'll call this withdraw function, which we might make public. So to implement this, it's quite easy. We're going to find the amount that's owed to that person. So we'll look up their balance, find the amount. Then what I'm going to do is actually send them some money. And there are different functions we can use to send. So we saw transfer before. But when you want to start getting more complicated with your interactions with other contracts, and when you don't know what the other contract's interface is, so you don't know if this is a token or if this is just a person on the blockchain like me or a Leaf or anyone like that, what we're going to use is the call function, which is the most kind of generic way of interacting with our smart contract. So this call function is available on any payable address. In this case, I want to send money to whoever has called this withdraw function, and I want to send the amount. So I'm going to use call. And call is a little bit special in that it can also take in optional arguments, which are in parentheses. And this is a very confusing design decision by whoever created Solidity, so apologies for that. But the optional parameters go in these parentheses. In our case, what we're interested in is how much money to send. So I'm going to specify that as the value. So we're going to call the contract or the address or whatever interacting with, send along the amount they have available to withdraw. And then in these brackets, I send any data that I want to send to that person at the same time. In our case, nothing. So you can see how this call function is really useful if you were interacting with another contract and you wanted to both send money and also call a certain function or add data to the contract. You can kind of do both at once. And stop me if any of this is confusing, because I'm happy to go through it as well. Now, this call function returns 2 values. So previously we've only seen functions that return 1 value, but this returns 2. And just like when we assigned multiple variables, I'm just going to save them like this. The first variable it returns is whether or not the call was successful. And the second is any data that calling this smart contract or this person has actually returned back, which is just like a byte array. So it could be anything, right? That looks like that. So hopefully that makes sense. What we're interested in only is the success variable. I'm going to say if the sending was successful, then we'll set the balances of the sender to be 0. Okay. It's just going to warn us that we're not using return data. That's fine. We don't care about it, but we do have to specify it. So we'll just leave that for that. So this is a really simple contract, and it is, from a user perspective, it is correct, right? When we withdraw, we check how much money someone is owed, we try and send it, and if the send succeeds, then we'll make their balance equal to 0. They've completed their withdrawal. But it violates that conditions affects interactions pattern. This is actually interactions and then effects. Right? So it's the wrong order. And what that means is this withdraw function is now vulnerable to the reentrancy attack. In this case, because it's such a simple contract, we can kind of only see one way of attacking it. And as someone who is attacking this contract, maybe what I want to do is I want to withdraw more than my fair share. If we're splitting 100 Ethereum between 4 people, we're each owed 25 Ethereum. But because we've got this order wrong, there is a way for me to withdraw all 100 without, causing this transaction to fail. And I'm going to demonstrate that using a second smart contract. And I hope that this isn't too confusing, but if it is, we can go through more examples because it can get a little bit tricky. But it's really important to understand when you start building your own applications because it's a very common attack. Now, the kind of thing that causes this attack to be possible is that when you call a contract, so when I use this .call here, and I send it money or any data or anything like that, you're essentially handing over control to that contract. It can run a function, it can compute some return data, and it will give you back control. And that's awesome. That means you can call a function and get values back. That's what let us do the transfer from in that split bill example. But it also means that in that period where the other contract has control, it is now able to do whatever it wants. And it kind of still has the potential to attack this contract once you've handed over control. So what we're going to do is we are going to put ourselves in the mind of an attacker, and we're going to write a contract which, when it calls withdraw, will attack this contract and will drain it of all the money in the contract. And to do that, I'm going to create a new one. I'm going to call this one attacker. I'm going to call this contract attacker. And it's going to start off like this. So this is the bad contract, right? I'm an attacker. I want to hack this share cash contract. And I'm going to just import share cash so that I can interact with the share cash contract. Okay, so what am I interested in here? I'm interested in the contract that I want to attack, which I'm going to store in a variable here, which is of type share cash. So just like for the ERC20 token, I can store an address here that is any contract that has the same interface as share cash. So it has a withdrawal method. And I'm going to make a helper function that will let me set that, that address so that I can deploy this attack contract. And then later on, when I know what contract I want to attack, I can set it in here. Now, what I want to do is I want to allow this contract to withdraw on my behalf, right? So it should call share cash and it should do the withdrawal for me. And so far, this is all fine. You know, this is a completely normal use of a smart contract. Maybe I don't want to reveal who I am, so I want a contract to take the money on my behalf. What I've done is I've made a new function called withdraw. I'll call this one withdraw for me, so it's not confusing. And all it does is it accesses the share cash contract at the address we've specified, and then it calls the withdraw function on that contract. So it will call this one here, and it should cause the share cash contract to send money to the attacker contract. Okay, and that's great. Are there any questions so far? I'm about to show the attack bit. Okay, cool. Now, what I can do and what any smart contract developer can do is they can add a new function into a contract that will run anytime it receives money. Right, and this can be really useful if you want to, say, stop people from sending money to your contract. Say there's no way to get it out and you want to just be really doubly sure. You might add a function that runs when you receive Ethereum that reverts the transaction, so you can be safe. To do that, just like the constructor is a special named function, we have a special function called receive here, which we declare like this. So it's a payable function, it can receive money, and this will be called anytime we receive Ethereum. So if we wanted to make it so that this contract couldn't receive any Ethereum, we might go require false, and it would fail anytime someone sent Ethereum to it. So that's the most common use case. What we're going to do is we're going to use this receive function here to attack the share cash contract and drain it of funds. And to do that, we will kind of draw a little diagram. So let me create a new diagram. Now I'm going to call this one, this can be my balance. So it starts off at, say, 100. And this is the share cash contract. Then I have my attack. So first of all, we withdraw. We call withdraw. Right? And then the balance contract here, or sorry, the share cash is going to send back our share of it, which is 25 Ether. Right? So far, so good. That makes sense. But when this attacker receives the Ether, that receive function runs. Because we've handed over control to the contract that's receiving Ethereum, this receive function runs, and it can do anything it wants. So what it's going to do is it's going to call withdraw again. So from within this receive function, we're going to do exactly the same thing, and we're going to call withdraw again. So now that we are calling withdraw again, in our diagram, we're going back to this contract and we've asked to withdraw. Right, so this is all within the same transaction. Now, if we look at our share cash contract, we can see that we are now back in the withdrawal function. So we're in here for a second time. We check the current balance of the contract, which might be 25, and then we pay it again. The issue is that this should be zero now because we've already called withdraw once. We've already been sent $25. But because the balance is only set to zero after the money has been successfully sent, we are now re-entering the withdrawal function before it's set to zero. So the second time I enter withdraw, the balance is still 25, and this contract will happily still send me another 25. Then, because it's called me, my receive function runs again, and I'm going to call withdraw again. And then I'm going to call withdraw again. And I can keep looping until this contract is completely empty. So instead of just being able to withdraw 25, I keep re-entering the withdrawal function, and I'm pulling 25 each time until the contract is empty. So we can see that because we've got that wrong order where the interactions, so the interactions are anything that kind of hands over control to someone or a contract external to this contract, which we can't control. Because that's happening before the effects, the conditions are no longer enforced. So that's not a good thing to happen. Because our generous smart contract creator has now lost all their money. And you might remember back at the start of this course, we talked about the importance of smart contracts being bug-free and some of the big hacks that have occurred in Ethereum history. So the DAO hack, which was the biggest hack to date, was something like $400 million worth of Ether was attacked. And what actually happened in the DAO hack was a really simple re-entrancy attack. So someone was able to withdraw their money that they'd invested into this decentralized autonomous organization, but they got their conditions wrong, and the person was able to keep going back into that function, keep re-entering it, and drain all $400 million out of that contract. So this is a super common, real world and very devastating attack that you need to know how to defeat. Okay. Are there any questions about the attack before I show you how to defend against it? Cool. And during the week, you might, because I'll send around these contracts, you might want to try actually deploying these yourselves in the Remix environment and running this attack and making sure that you kind of understand how it works. And then try the fixed versions of the contracts to make sure that it's all good. Okay, so there's kind of two ways that we can solve this. The first is to put our effects and interactions in the right order. So what we want to do is make sure that even if someone re-enters this contract, so it's withdrawn once, we hand over control in this line here, where we're calling the external contract. We want to make sure that if we re-enter and go back into the withdrawal function, we can't withdraw more money. So to do that, what we can do is move our effects above the interactions. So we're going to change it so our effects are up here. And we're going to firstly set the balances to be 0. Right, like this. So we've saved the amount that we're sending. We don't need to keep balances message.sender to be that value anymore. We'll set it to 0, and then we'll do that call. Then if someone comes back into the withdrawal function, it's only going to be sending them $0 from there on out because we've made that effect happen before the send line. Right, so that's now safe. Then the reason we kind of have this success variable is to make sure that if the sending fails for some reason, we don't withdraw their money. So what we can do is we go, if it's not successful, we'll kind of reset that balance to be whatever the amount we tried to send was. So you can see how we've kind of inverted that order. We've kept our effects at the start, and that's completely defeated the re-entrancy attack. So this is now in the right order. Okay, so that's awesome. That's one way of defeating the attack. And in a really simple contract like this, that might be the easiest way and the best way. And in general, just try and do your effects before your interactions, and you won't really have to worry about re-entrancy attacks. But in more complicated smart contracts, it can make the code quite messy. And there can be kind of situations where re-entrancy attacks emerge from having multiple functions that can be re-entered into in a certain order that becomes really difficult to reason about. So the other thing we can do is we can block this function from being re-entered at all. What we've done here by putting the effects and interactions in the right order, we've kind of made re-entrancy harmless, but we haven't prevented re-entrancy. So the alternative to fix is we can leave our code as it was. So I'll put it back into the wrong order, which looks like this. This is, again, the flawed contract, which can be attacked. And we're going to change this withdrawal function so that it can only be called once within a certain transaction. And to do that, we're going to use something called a re-entrancy guard. a common kind of search term that you can use if you want to look up this pattern. You might also know it from regular development, application development, as a mutex, which stands for mutually exclusive. And the idea is that once you've been into the withdraw function once, we've kind of got a exclusive lock on that function, which means that if you try and call it again, you can't get access to it. So to do that, we're going to do this as a modifier. So because we might want to use it on a bunch of functions, we're going to create a new modifier called reentrancy guard. And we're going to use this to decorate our withdrawal function. It should be as simple as this, and then it will allow it to only be called once within any transaction. But what we need to do is implement this reentrancy guard. And to do that, we'll have to kind of keep some state in our smart contract as part of the transaction. So we kind of have two states, right? We have not entered, so withdrawal hasn't been entered as part of this transaction, or entered, it has been entered. And we could kind of implement this as, say, not entered is 0 and entered is 1 and store it in a uint or just an integer. But Solidity has a handy feature that in a lot of programming languages let us give names to these numbers, and that is an enum. So enum stands for enumeration, just like the struct that we looked at for bids. It's a way to define kind of a new type within our smart contract. So going beyond the basic types like address, integer, bytes 32, we're going to define a new type now, which is an enum. And we'll call this one entry status. And then it uses the same curly brackets as a struct, but here we can list all the values that an entry status can be. So it's either not entered or entered. Now, behind the scenes, Solidity compiler might make these equal to 0 and 1, but from a development perspective, it's a lot easier to read not entered than it is to read 0. And if you're using it all throughout your code, it makes the code a lot more understandable. So what we're going to do is we're going to store the current entry status of the withdraw function for the transaction. So we'll have this new status variable, and it starts off as not entered. And you can see that to set a variable to be not entered, we just go entry status, the name of the enum, and then the value. So we're starting off as not entered. In the reentrancy guard, it's quite simple now to implement. We do a require, and we're going to check that the current status is not entered. And if it has already been entered, then we don't want someone to be able to call again. So we'll just say your reentrancy has been blocked. Right, that's really nice. Now what we want to do is we are going to enter for the first time. So if we've made it through this condition, we're ready to go into the withdraw function. So we'll set our status to be entry status.entered. We'll call whatever function we're modifying. So we just use the underscore. And then we've left that function. Everything has run successfully. So we can kind of reset back to not entered. And what this means is if we kind of trace through the withdraw function, if someone, like our attacker contract, calls withdraw, we're starting off by default in not entered. So we'll pass this condition. Then we'll set our status to be entered. Then we'll come into the withdrawal function. We will find out the amount to send. We will call the attacker contract. And then when we hand over control, it's going to try and call withdraw again. But it gets up to here, and this condition is now false. So status equals entered now, not entered. So the whole transaction will revert and the attack will fail. And so then using a reentrancy guard is a really easy way to kind of add insurance that you haven't made an ordering issue or you haven't made a reentrancy bug appear in your function, because it just stops people from being able to reenter in the first place. Any questions on that? Okay, cool. So in summary, a reentrancy attack is any kind of attack where you can call a function multiple times when it interacts with you, so that you can defeat the conditions of the function. So in here, we're defeating the withdrawal limit, essentially. And you can get around it in two ways. The first is to make a reentrancy harmless. And to do that, you put the effects and interactions in the right order. The other way is to make reentrancy forbidden, which is using that reentrancy guard. So you kind of put that like this. Correct ordering, effects and interactions, or reentry impossible. Cool. So we don't have a heap of time left. What I want to do is kind of preview what we'll be doing for the majority of the rest of the course. And that's starting to develop real applications, kind of like a project-based style. So I think the way it will work is next week we'll do another session like this, and we'll end with describing a really simple to start with smart contract that's kind of a real world use case. And what I'll do is provide the interface for it. So it'll just look like this. It's got the function signatures and the events. And I'll describe what that contract does. And then you can kind of take home or take to work the interface. And then it's kind of the assignment is to implement it and to fill this out, to test it in Remix, run the debugger if you need, and so on. And I'll show you how to use the debugger a bit more. And then we'll all get back together and we will review the code. So when we're doing smart contract development, it's really important to get as many people to look at your code as possible. And this process is generally called auditing or smart contract auditing, just to make sure there's no bugs, everything is as clear as possible, because once we deploy that application, it's there forever, right? And if there's a bug, you're in trouble because there's no way to fix it. So that's what we'll be doing. And I'll work out what scenario to use. I haven't kind of decided yet, but we'll do that next week. We'll also start to talk about more parts of smart contract development beyond writing the code. So the debugger is one of those things. I've kind of showed that off briefly, but there is really powerful debugger in Remix that lets us kind of step through our function execution, look at variables within the transaction and kind of work out bugs. And so I might come up with a few buggy contracts and show how to use the debugger. The other thing that we haven't looked at all is we have an inbuilt testing framework. So we can use this to write smart contract tests in Solidity, which are going to exercise all the different functions of our smart contracts and find any bugs. Just another thing. And we also have some automated testing tools, which can kind of analyze your smart contract and find common attacks. So there might be a tool that can find reentrancy attacks or simple reentrancy attacks and warn you, even if you haven't written a test or found a test case that covers that scenario. So that's also kind of a good part of the smart contract development process. And we'll get into all of that from next week. But what I wanted to show to kind of round out today is that a lot of the work in terms of building really simple smart contracts has been done for us, right? And the community is building contracts constantly and is kind of settling on standard ways to do things and standard code that you can reuse when you build your own applications. And one of those kind of code libraries that's really useful, and then I would recommend you check out, you see how they write their code, you see what kind of functions they provide to smart contracts. It's called OpenZeppelin. You see, I've looked at their reentrancy guide today. So this is OpenZeppelin like the blimp. And what they do is they build a library of smart contracts, which is contracts here, that is, as they say, battle tested. It's used by a lot of people. So at my company, right, we've built a blockchain application for agriculture, and we've based some of our contracts on these OpenZeppelin contracts. They're all open source and kind of shareable, free licensing and so on. And if we kind of go to that Solidity repository, and we'll go into this contract section, we can see they're covering an awful lot of functionality. So for example, if you're building out a token, you could write a token yourself that meets that ERC20 interface, or you could have a look in the token directory of OpenZeppelin. You can see they've already got an ERC20 folder, and you can see that they've built for us an ERC20 token that meets that interface with all those functions implemented, with good documentation as well, that you can kind of use as a basis for your token. And you can modify it and so on, but it's really helpful. They also have good documentation, which should be somewhere. There's the docs. Here we go. The docs site. Cool, yeah. So all their contracts are documented. Like this is the ERC20 token. It'll tell you information about how it works. And then as well as kind of these full application contracts, like a token, they also have little mini contracts that you can use as part of a bigger contract to add certain features. For example, if we go to the utilities over here, we might have, what have we got? Maths, we don't need to worry about that. There's a re-entrancy control one that I'm trying to find. This one right here. Aha, here we go. So it's in the security section. They've got a re-entrancy guard contract that you can just use as part of your contract definition. So they've already implemented that modifier, which is they've called non-re-entrant. We call it re-entrancy guard. And so that code is available for you to use whenever you want, right? And you can go to the source code of it, which is accessible somehow. Put this on GitHub, let's see. Yeah, here we go. Right, and it's all just here. So I've based my re-entrancy guard on theirs, except they've used integers to store not entered and entered, whereas we used an email. So you've got re-entrancy guard, you've got pool payments. Pool payments is that withdrawal method that we've been using. So they've implemented that for you. They've got contracts that can be paused. So if you find a bug, you can pause the contract while you work out a way to fix it or to recover. They've got a whole system for access control where you can have admins and super users and viewers rather than users and so on. So that's all built in. And these aren't suitable for every application, but it's always helpful to have a starting place. So I guess where I'm going with that is this week, before we kind of get into the project-based work from next week onwards, maybe have a look at OpenZeppelin and just see the sort of contracts that are available there. I'll send through these contracts that we've worked on today, and you can try deploying them in Remix. Try running that re-entrancy attack as well and seeing what happens there. But otherwise, we'll kind of regroup next week and talk about how the projects will run and go through some of that other stuff. So yeah, any questions before we wrap up?
Adel, I had a question.
Yep.
Do we have any assignments for this weekend?
No, it's optional if you want, is to try and deploy the share cache contract and run that re-entrancy attack on the flawed contract.
Okay, okay.
And I'll send the attacker as well, so you can just do that all within Remix. But then from next week on, we'll start doing proper assignments. No stress, but.
Project-based assignments, right? Project-based.
Oh, that's right.
Okay.
Yeah.
Thank you.
All good. I will stop the recording.